This video marks the release of an improved version of the Micro-Manipulator hardware. It includes a more detailed and consistent FreeCAD model, including all pins and fasteners, and also fixes a couple of mechanical issues. The biggest change, however, was made to the design and manufacturing process of the ball joints and linkage rods. Thus, the video will focus on these components specifically. The goal of the redesign is to reduce friction and tighten tolerances so the real device matches the microcontroller's kinematic model more closely. This reduces unwanted end effector rotation and improves overall positioning accuracy. As you can see here, the old pipe design has a very low contact area with unfavorable contact angles, leading to unnecessary friction and reduced stiffness. The new design uses a spherical socket instead, creating a larger and more uniform contact surface that distributes loads evenly and improves lubricant retention. Additionally, the 3D printed ball mount plate was replaced with a PCB, leveraging its superior material properties and precise manufacturing process. After the rod blanks have been prepared, both ends need to be chamfered. To produce a consistent taper on each end, we start by making a 3D printed tool for the job. The backside of a utility knife blade will provide the cutting edge of the tool. To reduce the risk of injury, the original blade edge is dulled first using sandpaper. Next, the cutting edge is formed. It is essential to orient the blade as illustrated here. The edge should be sharpened to an angle of roughly 30 degrees. The prepared blade is now pressed into a 3D printed holder. A screw in combination with the slots allow for precise vertical adjustment of the blade to produce the desired chamfer size. The tool is now finished and can be adjusted using a test rod. While spinning, the rod is pushed into the tool until it hits the backstop. Here, the chamfer is too small and the blade is adjusted accordingly. The goal is to machine the end surfaces to a diameter of approximately 1 millimeter. Now, all 6 previously prepared rods can be chamfered quickly with low effort and repeatable results. As you can see, this method produces very consistent results without the need for a lathe or other machine tools. The rod ends are now prepared for manufacturing the ball joint sockets. The sockets are formed by embossing a hard sphere into the softer brass rod ends. In the tool, the same balls used in the finished joints also serve as forming dies, ensuring the rod ends match the exact curvature needed. To locate the balls precisely at the center of the rod ends, a centering sleeve is built. A small PCB or metal sheet with a hole centers the ball in the embossing tool. Note that softer materials like PLA do not work here as they deform too much under load. A chamfered rod helps with centering the disc exactly with respect to the bore during gluing. After the sleeve is finished, the embossing ball is added. A tiny amount of glue prevents it from falling out during handling. Note that you can use a piece of scrap PCB or a metal sheet, but the thickness must be smaller than the ball diameter. To press the dies into the rod ends with good control and to set the desired length precisely, a digital caliper is used, both as a tool and as a measuring device. Since the caliper may experience some mechanical stress, I recommend using a dedicated unit for this task. Hardened steel calipers like the one shown here are widely available at reasonable low cost. To transmit force into the sloped edges of the caliper jaws, a set of 3D printed clamps is attached. A rod blank is then inserted into the guide block, and the 2 embossing dies are attached. The guide block also prevents the rod from buckling. It snaps onto the caliper, holding the rod securely during the embossing procedure. Note that the balls within the dies directly touch both the rod ends and the caliper jaws, allowing for precise measurements. A rubber band can be used to preload the caliper and produce a consistent measurement force. Using a hammer, the ball sockets on the first rod are carefully embossed to a depth of about 0.2 millimeters. A vise or a press can be used alternatively. The first rod serves as the length reference, and the caliper is zeroed accordingly. The other 5 rods can now be embossed to exactly the same length. Here you can see the rod ends before and after embossing. We now have 6 linkages with beautiful, uniform, and cleanly formed ball joint sockets. With the presented technique, length errors within plus minus 0.01 mm can be achieved. In this section, a simple friction measurement is performed to compare the old and new design. A spring-loaded clamping block is employed to preload rods equipped with the 2 ball-bearing types. The load on the lever is gradually increased until the friction within the ball joints is surpassed. The old ball joints held 24 grams in this test. As mentioned previously, the shape of the improved ball joints can retain dry lubricant very well, reducing friction significantly. Here, tungsten disulfide is used. The new ball joints yielded at about 2 grams, indicating roughly a 10-fold reduction in the friction coefficient. Let's take a closer look at the assembly of the ball joints and linkage rods. First, the balls are bonded to the ball joint plate, a small PCB that provides precise positioning of all holes and features. It also serves as a rigid base that, unlike the previously used 3D printed plastic, does not deform under the point load generated by the small balls. Due to the small size of the balls, proper bonding is critical. Storing them in acetone ensures a clean, grease-free surface for reliable adhesion. The correct choice of adhesive is also important. Use either a slow-curing metal epoxy, such as JB Weld, or cyanoacrylate, superglue, though the latter tends to perform slightly worse in this application. Next, the preload rubber bands are attached. Unlike the previous design, small jewelry crimp beads secure the polyurethane rubber bands. These are inexpensive and readily available online. Alternatively, short sections of 2 mm brass tubing can be cut and serve the same purpose. Make sure the rubber band extends about 1 mm for good grip. The ball joint is now complete. It features very low friction and, thanks to its preload mechanism, zero backlash. Its design is not only a crucial component of the Open Micro-Manipulator, but can also be implemented in other parallel kinematic mechanisms. As always, all design files and tools are available on my Github page. For those who made it all the way to the end of the video, I'd like to finish with a completely unnecessary, but fun, mechanism that automates the length adjustment of the linkage rods. To use the machine, a reference rod is loaded to set the desired length. During initialization, the machine first searches for the point where the drive nut touches the sled, then backs off and takes the reference length measurement. A fresh rod blank can now be loaded for embossing the ball sockets. The machine now presses the dies into the rod, backs of, and takes another length measurement with a controlled force provided by the springs. This is repeated until the length error is sufficiently small. The contraption successfully automates the length setting process and produces ball joint linkages with very low length deviations.